Welcome to the ARSET training, Sea Level Change Tools for Planning and Decision Support. It's great to see so many of you joining us today. My name is Sean McCartney, an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the first part of this two-part training on sea level change. For those that are new to ARSET trainings, the following slides provide a brief overview of the program. ARSET is an acronym which stands for the Applied Remote Sensing Training Program. ARSET is part of NASA's Earth Action Capacity Building Program, providing accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, tools, and applications. The goal of our trainings is to increase the use of Earth science, remote sensing, and model data in decision-making through training for professionals in the public and private sectors, environmental managers, and policymakers. On the right of the slide, you can see all the different thematic areas in which we conduct our trainings. Trainings are offered online and in person, and targeted to beginners and advanced practitioners alike. Trainings are freely available and conducted live instructor-led or self-guided, such as our newly released Fundamentals of Remote Sensing training on ARSET's Learning Management System. ARSET trainings are cost-free with materials offered in bilingual languages and are freely available to use and adapt to your curriculum. If you use the methods and data presented in ARSET trainings, please acknowledge the NASA Applied Remote Sensing Training Program. If you want to learn more, please visit our website. The following slides provide an overview of the two-part webinar series, Sea Level Change Tools for Planning and Decision Support. So why would somebody want to take this training? Well, Earth's seas are rising because of a changing climate, and this rate is projected to increase over the next century. Due to the warming atmosphere and ocean, ice sheets and mountain glaciers are melting, resulting in the addition of fresh water into the ocean. Ocean water expands as it absorbs trapped heat, causing sea levels to rise. Data on this increase in the rate of global sea level rise is critical to planners understanding the trajectory of future sea level rise. By the end of this two-part training, participants will be able to identify underlying Earth processes contributing to relative sea level change at global and regional scales, recognize remote sensing and model data used for assessing sea level change on a regional to global scale, describe how coastal communities and infrastructure can be impacted by flooding caused by sea level change, demonstrate how to assess the processes contributing to past and future sea level change with the Sea Level Explorer tool at global and regional scales, demonstrate how to access future projections of relative sea level change under different emission scenarios with the IPCC AR6 projection tool, and visualize oceanic and groundwater flooding maps with the Pacific Islands flooding tool. The prerequisite for the training is our Fundamentals of Remote Sensing course. We recently relaunched a new interactive, online, self-paced Fundamentals of Remote Sensing training on the ARSET Learning Management System, and we hope you will check it out and share it with your colleagues. Over these next 2 weeks, from June 10th to June 17th, there will be 2 1.5-hour sessions, which will include presentations, demonstrations, and question and answer sessions. All materials and recordings from each session will be available from the training webpage. If you are not able to attend one part, a recording will be made available within 48 hours on the ARSET training webpage. Homework opens on June 17th, 1 week from today, and will be due on July 1st. You will be able to access the homework from the training page on June 17th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. Part 1 of the training is focused on providing an overview of sea level change, both regional to global. The objectives for Part 1 of the training are as follows. By the end of today, participants will be able to identify underlying Earth processes contributing to relative sea level change at global and regional scales, recognize remote sensing and model data used for assessing sea level change on a regional to global scale, describe how coastal communities and infrastructure can be impacted by flooding caused by sea level change, and demonstrate how to assess the processes contributing to past and future sea level change with the Sea Level Explorer tool at global and regional scales. Prior knowledge that will help in understanding the concepts presented in this training are as follows. Satellite radar altimetry is a form of active remote sensing that measures the altitude of a surface from orbit by emitting radar pulses and measuring the time it takes for those pulses to return after reflecting off the surface. Satellite laser altimetry is a form of active remote sensing that measures the altitude of a surface from orbit by emitting laser pulses and measuring the time it takes for reflected pulses to return. Subtle shifts in Earth's gravity occur, primarily dominated by water movements from one place to another on and under land, in the ocean, and in the atmosphere. Satellite gravimetry is a method of remote sensing which uses a microwave ranging system where satellites that follow each other closely in orbit send microwave signals to each other to measure the distance between them. From distance measurements between two satellites, data can be used to estimate Earth's gravity field to monitor changes in underground and surface water storage, soil moisture, ice sheets and glaciers, and sea level caused by the addition of water to the ocean. Please put your questions in the questions box, and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the Q&A session after the presentations have concluded. The remainder of the questions will be answered in the Q&A document, which will be posted to the training page about 1 week after today's training. It is now my pleasure to introduce the guest trainers for today's webinar, Dr. Angelica Rodriguez and Dr. Denis Felikson. Dr. Rodriguez is a research scientist in the Sea Level and Ice Group at the NASA Jet Propulsion Laboratory, as well as the Project Applications Lead for the NASA Surface Water and Ocean Topography mission. Her research focuses on regional to nearshore ocean dynamics using in situ and remote observations, along with numerical models. She supports data-informed, equitable decision-making that uplifts vulnerable communities through both basic and applied research relevant to coastal resiliency. Dr. Felikson is the Deputy Project Scientist at NASA's ISAT-2 mission at NASA Goddard Space Flight Center, as well as the lead of the Integration Working Group on NASA's Sea Level Change team, and co-lead of the Greenland Ocean Forcing Focus Group for the Ice Sheet Model Intercomparison Project for CMIP-7. His research interests focus on combining observations and models of Earth's ice sheets to understand the processes that drive their change and to improve projections of sea level rise. Angelica, over to you.
Thanks, Sean. So as Sean mentioned, I'm Angelica Rodriguez. I am a research scientist at the Jet Propulsion Laboratory and a member of the NASA Sea Level Change Science team. Around the world, media are highlighting issues for coastal communities that are exacerbated by an impinging ocean and changing mean waterline. For example, the BBC News has an entire section dedicated to sea level, or the height of the ocean. Here we see 3 top stories from the last year. We left pieces of our life behind. Indigenous group flees drowning island. 1 in 4 properties at flood risk by 2050. Low tide may never be seen again. So what exactly is happening? Today, we'll be getting into the details of the underlying Earth processes contributing to global and regional relative sea level change. We'll also go over remote sensing and modeled data used for assessing sea level change, and we'll identify how sea level change influences flooding at the coast. Global sea level is the height of the ocean surface averaged over all the world's oceans. This figure shows the annual cycle of global mean sea level. The colors start darker and get lighter with time. Each line shows the seasonal changes in the mean sea level. And were these lines to stack right on top of each other, there would not be a net increase. However, they do not, and indeed the lines reach higher and higher on the y-axis. Taking this same data and plotting the full record between 1993 and 2025, as is depicted now, we see there's a trend in the data. In fact, the rate of sea level rise has been accelerating, and the data indicates a nonlinear increase in the height of the ocean. Because NASA has been measuring this quantity for over 30 years, we have an incredibly valuable metric of how the Earth's climate system is changing. The main instrument that directly measures the height of the ocean is called a radar altimeter. NASA refers to the satellites that employ this observational technique as ocean topography satellites. Just as the terrestrial surfaces have highs and lows, so does the ocean. Radar altimetry operates by transmitting radar pulses directly downwards, sometimes referred to as at nadir, and measuring the time it takes for the pulse to reflect off the surface and return to the satellite. It essentially measures the range to the closest point on the surface within a relatively large footprint. Data is collected along a narrow strip directly beneath the satellite. The observation is provided publicly in a geocentric reference frame and provides a measure of absolute sea level. Through interpolation techniques, we can see how the global oceans are changing in height across the world. NASA has been measuring sea level for decades now. The series of satellites shown on the right all contain radar altimeters. The Sentinel-6 Michael Freilich mission, which launched in November 2020, is the latest in the series of satellites that have contributed to the sea level record. Sentinel-6B, its predecessor, will be launching later this year in 2025. Our most recent accounting indicates that since the beginning of the record, global mean sea level has risen by 10.5 centimeters, and the rate of annual sea level rise has more than doubled. 2024 marked the sixth largest increase in global sea level in the 3-decade-long record. As the panel on the top right indicates, the 2024 annual mean sea level rose relative to the 1993 to 2023 climatology, or long-term average, almost everywhere in the global ocean, albeit with differing magnitudes. This point about regional variability is underscored in the bottom two panels, which show the change between 2023 and 24 to the left, and the year of maximum sea level experienced at a given location on the right. With a planned launch in November 2025, Sentinel-6B will continue to measure surface height down to a few centimeters for about 90% of the world's ocean, enabling NASA to continue observing ocean height for years to come. And this is important because we all have the question, will this continue? And to answer that, we need to observe sea level and we need to know what is the underlying cause of this phenomenon. To lead with the punchline, we do in fact have a good handle on what's driving the changes in global sea level. Scientists have conducted analysis determining which pieces of the climate system are leading to changes in the global mean. With various means of accounting and our understanding of the feedbacks within the climate system, it is clear that increased greenhouse gas concentrations are increasing the global atmospheric temperatures. Much of this heat is going into the world's oceans. And as water heats up, it expands and takes up more space. Similarly, much of this heat is going to melting ice sheets and glaciers, which are directly adding water to the ocean. According to the most recent budgets, about 2/3 of global sea level rise is due to melting ice, while 1/3 is due to melting or to increasing ocean heat content. Additionally, changes in terrestrial water storage, or how much fresh water is transferred from the land to the ocean, can also influence the global sea level, but in much smaller percentages. NASA has a number of satellites that are able to give us information on the various pieces of the puzzle. The ISAT-2 mission provides a key observation of elevation of ice. ISAT-2's laser has a high sampling rate of 0.7 meters along the track and a narrow footprint of only 14.5 meters, and near global coverage, repeating every 3 months with a 6-beam geometry that enables instantaneous cross-track slope determination. So as the laser sends thousands of pulses of light to the ground each second, a small fraction of those photons bounce off the Earth's surface and return to the instrument, where the photon counting detector times their flight. This is similar to radar altimetry in that it is measuring the height of the surface, but the technique is much different. Using ISAT-2 data, scientists have provided estimates of height change across the largest masses of ice on Earth, the Greenland and Antarctic ice sheets. As you can see on the left, the height change along the Greenland ice sheet's periphery is drastic. So as snow may accumulate on the interior of the ice sheet, it is being quickly eroded away or melting at the edges. On the right-hand side, the Antarctic ice sheet is experiencing hot spots of height change as well. This is primarily along the West Antarctic ice sheet in the Amundsen Sea and Bellinghausen Sea sectors, and parts of the East Antarctic ice sheet along Wilkes Land. The GRACE-FO satellite mission is another way that we can track changes in ice contributions to sea level. In contrast to the previously discussed satellites, the GRACE mission operates with 2 satellites trailing one another. They do not send pulses directly down to Earth, but rather they operate through tracking the distance between the 2 satellites with a highly precise microwave ranging system. As the leading satellite approaches a region of greater gravity, for example, a mountain, it is pulled a little bit farther ahead of the trailing satellite, slightly increasing the distance between them. Then, as the lead satellite flies past the high gravity area, it gets pulled slightly back, while the trailing satellite, which is now approaching the gravitational mass or mountain, is pulled slightly ahead, narrowing the gap. These changes are tracked all over the globe and give an indication of the changes in gravity field, which can be converted into mass changes over time. The figure on the right-hand side shows similar patterns to the elevation change of the ice sheets. But here we're showing the actual rate of change in mass loss over the ice sheets. This is depicted as a time series averaged over the ice sheets in the line plot below. As you can see, both Antarctica and Greenland are steadily losing mass over the observational record. The GRACE satellite also provides measurements of changes in land water storage. And as I mentioned previously, this can be a non-negligible component to the global sea level change, and in fact, has a strong signal on the interannual variability in the global sea level. Satellites cannot directly measure ocean heat content. While we have long time series of ocean surface temperature, this is not the same as measuring the total water column integrated heat content. To do this, we must rely on in situ observations, such as the ARGO program's array of profiling floats. The ARGO float is a very critical observation tool for oceanographers, as it provides global pictures of how much heat is in the ocean, as well as the salinity content of the oceans. It does this through acquiring data at depth and giving a profile or depth varying observation of how the salinity and temperature are changing from the surface to 2,000 meters depth. The globally integrated ocean heat content is shown on the plot to the right, above 2,000 meters. And as we can see, there is a strong annual cycle, just as there is in the mean sea level, but it is also increasing. And we are confident in our understanding that this is largely a consequence of uptake of atmospheric heat transferred from the atmosphere to the ocean. Another tool in our toolkit to measure sea level and the attributed processes are tide gauges. Tide gauges have been used since the 19th century along US coastlines to measure local sea levels. Together, the tide gauges and altimeters tell us how sea level is changing both globally and regionally over periods from minutes, thanks to tide gauges, and decades when combined with satellites. While older tide measuring stations used mechanical floats and recorders, modern monitoring stations use advanced acoustics and electronics. Today's recorders send an audio signal down a half-inch wide sounding tube and measure the time it takes for the reflected signal to travel back from the water's surface. Both satellites and tide gauges have shown that sea level has risen almost everywhere over the last 30 years. Satellites measure the height of the ocean in a geocentric reference frame, while tide gauges measure sea surface height relative to land. So, where the land is moving, we can see big differences between the tide gauge measurements and the satellite observations. An example of this can be seen along the Alaskan and Canadian coastlines, where there's high amount of vertical land motion. So in order to compare these more directly, we have to account for the way that the land is moving. Vertical land motion can be caused by a number of things, including glacial isostatic adjustment, meaning the way that the land is adjusting to different loads of ice that are melting, tectonic activity, the surface mass loading changes, and other localized effects that can influence the way that the land is uplifting or sinking, such as groundwater extraction. There are other factors that affect local sea level as well, such as the way that the ice sheets are impacting the gravity, rotation, and shape of the Earth. These are referred to as ice sheet fingerprints. The figure to the left shows ice sheet fingerprints for both Greenland at the top and Antarctica at the bottom relative to the global average. The farther away from where the ice is melting, the more sea level rise that location will get. Areas, for example, that are far away from Greenland experience higher sea level change due to these gravity, rotation, and deformation effects than very near Greenland. In order to account for the total contribution, we have to combine the response for both Antarctica and Greenland. The way in which the ocean moves can also actually have an impact on how sea level is experienced along a given coastline. We refer to the combination of steric changes and dynamic changes as stereodynamics. So, steric refers to variations in sea level that are due to the changes in the density of the seawater, which are governed by the temperature and salinity. These have strong impacts on the regional variations in sea level, as different parts of the ocean are experiencing different rates of warming and changes in salinity. Ocean currents also play a crucial role in transporting heat and distributing seawater across the globe. The figure to the top is showing ocean currents colored by the temperature on the right and salinity on the left. As you can see, the changes in these colors can be drastic, even along a very small stretch of current. This data is actually not data at all. It is model output from the ECHO state estimate. ECHO is a NASA tool that assimilates all available observations of the ocean and conducts numerical modeling constraints to those observations and provides us a global picture of how the ocean is moving and what the water properties are. Here we're looking at a boundary current. These are places with high variability and the strongest currents in the world. Stereodynamics can act to change the sea level on a number of time and space scales. These dynamic changes involve the redistribution of water masses and can respond to different forcings such as winds and atmospheric pressure systems. ECHO is primarily used to diagnose changes in sea level on the interannual to decadal and secular timescales. That is shown here on this plot in the green oval on the years time scale and thousands to 10,000s of kilometers length scale. However, there are a number of additional processes that act on shorter timescales and smaller space scales, such as storm surges, changes in tides, tidal elevations, that is, river runoff, and wave setup. So, how will the average or mean sea level change in the future? Well, using our consensus knowledge of the modeled physical processes that can be observed and constrained using observations, as well as statistics informed by existing data records, we can project future sea level. The Intergovernmental Panel on Climate Change Sixth Assessment Report provides sea level projections built using comprehensive assessments of a wide range of processes, much of which we've covered here, um, to report different scenarios of potential future sea level change. The AR6 provides a probabilistic framework that accounts for both well understood mechanisms and some that are more uncertain. Later in this training, you will get into some of the tools that NASA provides, which leverage these projections obtained through the IPCC AR6. For example, here in Funafuti, Tuvalu, we're showing sea level in meters as a function of time for different scenarios given by the different colors. We can also partition the different processes contributing to these projected changes, such as the vertical land motion, land water storage, changes in the ice sheets and glaciers, and sterodynamics. And how do we expect these changing mean sea levels to impact our coasts in the future? Well, dynamic variations in local sea level, such as those referenced earlier, tend to combine. So the natural ups and downs that weren't a problem before could now be a problem with an elevated mean sea level. The year to year and monthly and even daily fluctuations of sea level driven by tides, storms, and waves, which once were not a problem, could become a problem. An example of this is high tide or sunny day, sometimes referred to as nuisance flooding. This typically occurs at a king tide or more frequently these days, just a large tide, and it doesn't even have to be the highest tides of the year. In contrast to storm-driven flooding, high tide flooding can be felt on just a regular day due to elevated background sea level and regular tidal fluctuations caused by the gravitational pull of the sun and moon. Tide gauges observe these changes and can give an indication of how severe the flooding has been over time and how it's changing. Using the Funafuti tide gauge as an example again, we see that water levels in Funafuti have exceeded half a meter on 138 days during the full 44-year record of observations. The maximum number of flooding days for this threshold during a single year was 14 days during 2021. And as you can see by the orange dots above the threshold line, these exceedances are occurring more as we go through time. In 2020, for example, we see over 10 days of flooding, given by the bar graph at the bottom of the slide. We can use mean sea level projections to project the number of flooding days in the future. Relying on the modeled physical processes and statistics available through the IPCC, we can pair our understanding of tides with expected ranges of sea level to determine potential increases in numbers of flooding days. This will be expanded upon in part 2. So increasing mean sea level can have far-reaching consequences. Flooding is an example of a direct impact from sea level rise. And in addition to this, there are other impacts such as saltwater intrusion, elevated groundwater, and landscape changes. These are direct physical processes that are occurring due to changes in the waterline. These direct impacts can have cascading impacts that include infrastructure and property damage, health risks driven by wastewater infrastructure challenges, economic challenges in dealing with how to respond to these inundation events, as well as habitat loss. Each community will indeed feel these impacts in different ways. And so it's critical to have many information sources that feed into the total risk calculation for a given community. Variations in coastal landscapes and environments, as well as social and economic factors and coastal development, all play a role in determining how sea level rise impacts are felt in the different locations. NASA has several tools that can provide some baseline information to take into consideration in determining a community's path forward. Using our novel observations and models, we provide our best estimates of some of the critical factors that go into handling and dealing with changes in sea level. And with that, I'll pass it off to Denis to talk to you more about some of these tools.
Thanks, Angelica. Hi, everyone. My name is Denis Felikson. I'm a research scientist at NASA's Goddard Space Flight Center. And this part of the training, I will introduce and demonstrate the Sea Level Explorer tool. So just as an overview before we get started, this training will actually present three tools in parts 1 and 2 that can be used to access sea level change information. The first is the Sea Level Explorer, which I'm going to present in this portion of the training. There's also the IPCC AR6 projections tool and the Pacific Islands flooding analysis tool, which you'll hear more about in part 2. The underlying data and projections are consistent across the three tools, and all of the information that the tools provide come from either peer-reviewed papers, assessment reports, or other federal reports. Here we'll focus on the Sea Level Explorer tool, which provides a high-level summary and synthesis of past, present, and future sea level rise, as well as impacts for coastal locations around the world. So the Sea Level Explorer tool provides information on both historical and future sea level change. Historical sea level change and contributions from individual components can be reconstructed by combining tide gauge records with satellite observations. The individual components that make up sea level change at any given location are shown here on the left. We have the inverse barometer effect, IBE, which is the influence of atmospheric pressure changes on local sea level. Glacial isostatic adjustment, or GIA. This is caused by the long-term effect of changes in the Earth's glaciers and ice sheets. Gravitational, rotational, and deformational, or GRD fingerprints, which result from contemporary changes in the Earth's glaciers and ice sheets. Stereodynamic sea level, which arise from changes in the ocean's circulation, temperature, and salinity. And vertical land motion, which can be caused by a variety of factors, including groundwater withdrawal and tectonic activity. When we sum up these individual components, we get an estimate of relative sea level change. That is the height of the sea surface relative to the height of land. This is what tide gauges around the world measure directly at individual locations, and satellite observations and models allow us to construct a global picture of relative sea level change, which is shown here in the top middle graphic. In addition to historical data, the Sea Level Explorer provides future projections of sea level change. These come from the Intergovernmental Panel on Climate Change Assessment Report 6, or AR6 for short, which was published in 2021. AR6 provides a comprehensive survey of our scientific understanding of sea level change and produces a consensus set of projections of future sea level change under a range of scenarios. The figure at the bottom of this slide shows the range of future global mean sea level change under these different scenarios. And as you can see, there's a wide range in uncertainty, both within any one individual scenario, denoted by the different colors, as well as across the different scenarios. In part 2 of this training, you will learn more about these projections, how they are developed, and how they can be interpreted. Now I'm going to switch to a web browser and show you a live demonstration of the Sea Level Explorer tool. All right, here in a web browser, I've navigated to earth.gov/sealevel, This is the landing page for the Sea Level Explorer tool. On this landing page, you'll see some introductory information about the data that's in the tool, as well as a list of the partners that have contributed to this tool. This effort was led by NASA, but also in collaboration with the DoD, the World Bank, the UN Development Program, as well as the US Department of State. So as we scroll through this landing page, we can see some high-level information about global sea level change. When we scroll a little bit further down the page, we have what we call these vital signs. These are metrics that indicate how the state of Earth's climate. You can see sea level is one such metric shown here in the top left. We can actually click on this plus and expand to get some more information about sea level and how it's changed since 1993. So this is sea level. These plots show sea level change information from NASA satellite altimetry, as well as historical reconstructions that go back further in time. This is where we bring in global tide gauge information to do that reconstruction, as I introduced before. So here's the satellite data on the left plot shown in orange. Again, you can see we were tracking it since 1993, showing the increase in global mean sea level change. On the right, this is a plot of just the satellite data over that period, and you can hover and get the actual underlying numbers underneath. These plots are updated regularly, so as you navigate to this page and bring up these plots, you should see the most up-to-date information about global sea level change. All right, closing out those plots and scrolling a little further, you can see this landing page has other high-level kind of introductory information about why sea levels are changing and how. I won't go through all of this in any detail, but feel free to browse this and scroll through it yourself. If I scroll back up, to enter the actual tool, we're going to use the Sea Level Explorer button here that's shown in blue. So when I click this button, another web page opens up, and this is the first web page for the actual tool, where we can select a location where we want to explore sea level change information. We'll start by looking at the global information that's in this tool, and we can access that by using this global average sea level rise link here at the bottom. When I click that, we get into our information page showing global sea level change information. So the first thing we see at the very top are some key points about global sea level change. So this is information about the global mean sea level all around the world. We can see some of the key points here, that sea level rose 10 centimeters from 1993 to present. This is coming from that NASA satellite altimetry record. We can see that in the future, sea level is expected to rise another 15 centimeters from 2020 to 2050. Again, this is as a global mean. And then after 2050, the key point here is that this is when we become heavily dependent on future emissions and warming. So again, in part 2, you'll hear a lot more about these different emissions and warming scenarios. But the key takeaway here from these high-level key points are that up until 2050, we expect a certain amount of sea level rise. And after 2050 is where the different scenarios start to diverge. Scrolling down a bit on this information page, we start to get more detail. So here is a plot that shows historical change. So again, this is the key point, that globally, from 1993 to present, sea level rose by 10 centimeters around the world. And we see a figure come up that actually shows a breakdown of this by month for any given year. So you can see how the seasonality of sea level works through time. Again, you can hover over this plot to get the different the values of the actual different data points, and we can even somehow download this plot. I think that we get it. Ooh, snapshot. Yes, there we go. The snapshot button. If you click the snapshot link, it will actually download the plot that you're seeing here. There is also an explainer explainer with a transcript here that will explain more details about the data that's shown in the plot. A lot of parts of this Sea Level Explorer tool will offer additional figures. So look for these show additional figures links. When I click on that, you can see some other plots that come up. This is the same data that we saw before on the earth.gov/sea level landing page that shows the global satellite altimetry record of sea level change from 1993 to present. And then this blue curve is the sea level reconstruction. This is where we bring in the tide gauge information to go back further in time, as I said in my intro. There's also, the data is also shown tabularly here. And then there are breakout boxes for additional information about how we measure sea level and specifically where the data that's being shown in this tool comes from. Scrolling down a bit further on this information page, this is where we can find information about future projected sea level. So this key point here up at the top, the title, says that under this particular warming scenario, SSP 2-4.5, we expect 15 centimeters of global mean sea level rise from 2020 to 2050. And then it also gives a likely range around that projection. So again, this is just for one particular warming scenario. And if we click this option button, we can actually switch to different scenarios. So if we, for example, pick this other scenario, SSP 5-8.5, this happens to be a much warmer projection, we see that we get more sea level rise. If I click this option button again, we can actually select by global air surface temperature warming level rather than scenario. Some users like to see their projections displayed this way instead of by scenario. So under 5 degrees warming, global air surface temperature warming, we expect to see 19 centimeters of rise. And you can change these options here. And you can also pick the projection year. So if you're interested in sea level at 2100 instead of 2050, you can select the year there, and we can see how sea level really starts to accelerate in the latter half of that the coming century, depending on the warming scenario. Okay, so if we scroll further down, we can see plots showing these different projections under the different warming levels. Again, you can hover to get the values of the actual data points underneath. You can take a snapshot as before, and there's an explainer with a transcript if needed. Again, we can click the Show Additional Figures link to expand the next section where we can find tabulated information. And again, we have these breakout boxes that give more information about how these data are put together and the specific data sources where they came from. So you can actually, these hyperlinks will actually take you to the actual AR6 published report where you can get much more detailed information and the original source of the data. All right, now I'm going to scroll all the way back to the top of this page. So here we were looking at this first tab of the tool called Sea Level Change. There are other tabs here that I'll step through, including high water impact, contributions, and next steps. The high water impact tab I'm actually going to skip. This is information that's only provided locally at individual locations and not as part of the set of global projections. So I will show you this in the next part of this training where I'll show you how to explore sea level change information for particular locations. So if we go to the contributions tab, this is where we get more information about how the different individual components are contributing to historical and future sea level change. Again, we have key points here at the top that summarize things. So from 1993 to present, this is the historical portion. We see that as far as global mean sea level goes, 60% was caused by changes in mass of the ice sheets and glaciers, and 40% by changes in stereodynamic sea level. Kind of as a rule of thumb, or as a general rule, vertical land motion does not contribute to global mean sea level change, but you'll see in the next part how it contributes locally to at different locations to relative sea level change. Okay, so that first key point is about the historical sea level change. This next key point is about the future. So in 2050, we expect about the same breakdown of ice sheets and glaciers, 60% coming from the land ice on Earth and 40% from stereodynamic sea level. If we scroll further down, again, we get more information that back up each of those key points. So here's the same statement for the historical 1993 to present, how things break down. We can also see a pie chart showing these different components over that time period. And if we hover, we get labels for all of these things. This pie chart actually breaks things down, breaks the land ice part of it down further into the Antarctic ice sheet, the Greenland ice sheet, and global glaciers, as well as terrestrial water storage and how changes in land water storage have affected global sea level over that time period. The additional figures will show that same information as a bar chart. And again, we get these breakout boxes that provide more information, as well as links to other resources. Here's a nice explainer of a short one that talks about specifically how that data is put together over the historical period, and again, with links to other references. All right, scrolling a bit further, this is where we get into the future sea level projections. So this is, again, a restatement of that key point above, that in 2050, 60% of future global mean sea level change will be caused by ice sheet and glacier change and 40% by stereodynamics. Here's where things can get interesting. If we open up the options and select different scenarios, for example, if I go out to, and different years, excuse me, so if I go out to 2100, you can see how things start to change. So under this very high warming scenario, we get more contribution from ice sheets and glaciers relatively to stereodynamic sea level. And if we select a lower warming level or a different scenario, you can see how the numbers here in the background change. Again, scrolling further, you can see more different ways of visualizing the same information. Here's a bar chart that shows the individual contributions in units of meters now. So this is not as a percentage, but shown in actual units of meters, global mean sea level change. And across the bottom axis here are different warming scenarios from the lowest emissions and warming to the highest. So you can see how the total global mean sea level numbers change as well as the different individual contributors. And again, we have breakout boxes that talk about how this data was compiled, as well as other references for the data. All right, now I'm going to go to the final tab here, which are next steps. These offer a couple of additional resources, excuse me, which will show you more information about how all of this data is compiled, as well as tools and content for educators that would like to incorporate this into their curriculum. Finally, one thing that I wanted to show is that there are two buttons here up at the top, Summary and Data, which will allow users to download a set of summary slides for the data that's presented. So clicking the Summary tab will open a new tab that provides some bit of explainer and a very high-level summary of the data that's shown in the tool. And the Data button will allow users to download the actual data that's that's underlying this tool. All right, next we will look at the same information, but at local individual locations. So if I click on this, there are a couple of ways to go back. One is to click the Sea Level Explorer tool link, excuse me. The other is to click this hamburger kind of menu, and this will pop up the location selection, and here's where we can select individual countries or other locations for local sea level change information. All right, in this menu, I'm going to select first a country. For this example, I'm going to pick a location in France. And then the second drop-down becomes active once you've selected a country. And this allows you to pick specific coastal cities or regions where you want to view sea level change information. Again, here I'm going to pick a specific place, Brest in France, and I'll click on the orange arrow to take us to the Sea Level Explorer information within the tool. So as you can see, the structure of the information here is going to be very similar to what we saw for the global mean sea level change information. We start with some key points, but now all of this data has been tailored to this specific location, has been localized to the location that we've selected, Brest, France. Key points here for Brest are that sea level rose 8 centimeters over the historical period, and we expect a rise of 15 centimeters in the future. This just coincidentally happens to be very similar to the numbers that we see for global mean sea level, but if you select other locations, you'll see different numbers here because, again, they've been tailored to the specific location. As we scroll, again, we will see similar plots, but for this particular location that we've chosen. If I open up these additional figures, we actually get more information here. We start to bring in the local tide gauge information in addition to the data that we saw before that comes from satellite altimetry and the global sea level reconstruction. So the green kind of very wiggly line is the local tide gauge data. And this plot here shows that there's very good agreement from these different methods that reconstruct sea level information, from satellite altimetry in orange, this historical sea level reconstruction that we do globally in blue, and the local tide gauge information that's in the background in green. So we have very good agreement, giving us a lot of confidence over how sea level here has changed in the past. We also, again, get this data tabulated in table format. Continuing to scroll, we get to the future scenarios. So here again, this is showing relative sea level change at this location in Brest, France. We can, as before with the global data, we can click on options and select different warming levels and different sea level change scenarios and years. So here I'll just change to 2100 to see how much sea level rise we expect over the next 80 years by the end of the century. The next plot will show again the same type of curves that we saw before, but for Brest, France, for this local place that we've selected. And additional figures show that same information that's tabulated. So here's I'll just point out this is where things can get interesting because as we saw with the global mean sea level, there was a big contribution from the ice sheets. A large percentage of global mean sea level was caused by ice sheets. But here in this particular location in France, we see that there's very little contribution because of ice sheet changes, and most of the cause of sea level change in Brest, France is due to stereodynamic changes in the ocean. And this has to do with how those GRD fingerprints react to ice mass change. I won't get into the details there, but you're more than welcome to read more in these Understanding Future Sea Level Change and Data Info and Sources references. All right, looking at the high water impact tab, this will give us information about local flooding caused by historical and future sea level change. So again, this information is not available as part of the global information, but when you look at local individual locations, you will see information here for some locations that have adequate data for us to be able to quantify this. So this particular example in Brest, France does have a tide gauge record that is long enough for us to be able to show how flooding has occurred in the past and how we expect it to change in the future. The two key points, again, we summarize what's happened in the past and what we expect to happen in the future. So this first key point shows that in the 1970s, there were 988 days that exceeded the local minor high water level in this location. And that ramped up to over 1,000 days in the 2000s. And then by 2050, we expect, under a certain warming scenario, that this location, Brest, France, will have up to 149 minor high water days per year. Scrolling down, we can get more information on this, as well as figures that show how this has changed over time. So here's a plot that shows the number of days per year that flooding is expected to occur in this location, where water levels caused by long-term and short-term sea level change exceeded a minor high water level here. If we expand the figures, we can see another visual representation of this. The x-axis here shows sea level relative to mean high water, minor high water, and that's what this black dashed line shows. And then the different curves show the probability that that threshold will be exceeded over these different number of years. I should say that in part 2 of this training with the Pacific Island flooding tool, you'll get a lot more information and a lot more detail about how this information is compiled and how it can be interpreted. So I'll just give a high-level overview here, and then you can watch the part 2 training that will give a lot more information about flooding and how sea level contributes to that. So scrolling down, we get the tabular information, and again, breakout boxes that can lead to other references. Here we have the future information. So again, under this SSP2 4.5 scenario, we expect, as I said before, up to 149 minor high water days per year in 2050. And if we change the year, we can see how that changes throughout the course of the century. Here's a chart that shows by year and by warming scenario how this projection changes with time. So you can see there's a steady increase in the beginning of the century, but a lot of the numbers look similar across the different scenarios, whereas towards the end of the century, we really get a lot more minor high water days in Brest, France under a high warming scenario than we would under a low warming scenario. So if I hover, I can see that under the lowest warming scenario, there's about 177 days projected in 2100 with flooding, whereas under the high warming scenario, the highest of the warming scenarios, we get 250 days. So a big difference in terms of how sea level can impact at individual local locations under different warming scenarios. All right, that's the high water impact tab. If I click to the contributions tab, again, this is very similar to what we saw with the global mean sea level information, but localized for this location. So historically, in Brest, France, we see that only 30% of sea level change from 1993 can be attributed to ice sheets and glaciers, 45% to changes in ocean stereodynamics, and 25% due to vertical land motion. So this is local motion of the land in Brest, France is contributing to about a quarter of the relative sea level change we observe. So in other words, as the ocean levels have risen, the land here has also subsided. And that is contributing to about a quarter of the relative sea level change that we see in this location. Looking forward to 2050, we expect much higher contribution, attributed to changes in stereodynamics than to ice sheets and glaciers, and a lower contribution from vertical land motion. Scrolling through, we can see more information. Again, we have this kind of pie chart where it breaks down the different components. So here, again, we have this new information coming from local vertical land motion, which didn't contribute to the global change, but does contribute to local information. And continuing to scroll, we can see how that breaks down in the future under different warming scenarios. So these are bar charts that show that in 2050, under different warming scenarios, how much we can expect each one of these components to contribute to local relative sea level change. As before, we can download a summary of this information as well as the data up here in the upper right. And then the next steps show you those same resources where you can learn more about sea level change as well as get tools and content for educators. That concludes our live demo of the Sea Level Explorer tool. In the slides are some additional resources that will provide more information about the underlying data, the methodologies that were used to compile the data, as well as some other resources. And we look forward to seeing you in part 2 for demos of 2 of the other tools. And I will now hand it back over to Sean for a summary.
Thank you, Denis and Angelica, for the wonderful presentations. The following summarize the concepts covered in Part 1 of the webinar series. Processes contributing to sea level change include greenhouse gases added to air by human activities, which then warms the planet. As oceans warm, they expand. Ice sheets and glaciers melt, adding water to oceans, all contributing to global sea level rise. Impacts of sea level change include high tide flooding, also known as sunny day flooding, and variations in coastal environments, social and economic factors, and coastal development all play a role in determining how impacts are felt in different locations by different communities. NASA's unique capabilities in both remote sensing and modeling include radar altimetry, laser altimetry, gravimetry, incorporating in situ data, and advanced modeling techniques. Finally, we had an overview and demonstration of the Sea Level Explorer tool, which provides a high-level synthesis of past, present, and future sea level rise and impacts for coastal locations around the world. Looking ahead to next week and part 2 of the webinar series, we will be covering the following topics: projecting future sea level change, the framework for assessing changes to sea level, or FACTS, an overview and demonstration of the Intergovernmental Panel on Climate Change 6th Assessment Report Projections Tool, and an overview and demonstration of the Pacific Islands Flooding Analysis Tool, which incorporates both oceanic flooding and groundwater flooding. Before we transition to the Q&A session, I want to remind you there will be one homework assignment which you will be able to access from the training page 1 week from today on June 17th. Answers must be submitted by Google Form with a due date of July 1st. To receive a certificate of completion, you must attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after the completion of the course. We want to thank once again Dr. Rodriguez from NASA's Jet Propulsion Laboratory and Dr. Felikson from NASA's Goddard Space Flight Center for their presentations today. Below is the contact information for Dr. Rodriguez and Dr. Felikson, along with links to the ARSET website and social media. If you enjoyed today's webinar, we hope you will sign up on the ARSET listserv to receive notifications for future trainings, and follow us on social media for other relevant announcements pertaining to NASA's Earth sciences. Below are a list of resources relevant to the material covered in Part 1 of the training. We will now transition to the question and answer portion of today's training. Please enter your questions in the question and answer box, and we will get to them in the order that they were received. We will post the Q&A document to the training webpage once we've finished answering and editing all questions. And we want to thank everybody that's been submitting. We've gotten some really great questions, so thank you to everybody that has submitted so far. And we do have, again, we have roughly 22 minutes left. So if you are thinking about submitting a question, please do go ahead, and we'll try to get to as many as we can in the remaining time. So jumping right into it, question number 1, is it possible to monitor ocean height in mangrove ecosystems when there is thick vegetation?
I can jump in on this one, Sean.
Great, Denis, thank you.
Sure. And so I have a short answer. This is a very good question, and I would say it's an open area of research. In general, it is possible where the vegetation is not sufficiently thick. So with satellite laser altimetry, the laser can actually penetrate through vegetation and make its way down to the surface of the ocean before it reflects back to the spacecraft. But where vegetation is thick, we don't get enough signal coming back from the ocean surface, and so we can't measure it. So it's kind of a general answer, but in short, it is possible in some places, but not where the vegetation is so thick that the laser signal can't penetrate down to the ocean. It's a great question. And this is where ground-based measurements like those from tide gauges are critical for us to be able to validate the measurements that we're getting from the satellite, because the tide gauges can directly measure ocean levels, whereas in some cases the satellite can't see all the way down to the ocean through the vegetation. It's a great question.
Great, Dennis, thanks so much. Question number 2, are the interagency sea level rise task force projections / scenarios being phased out? And whoever asked this question, we are unable to answer that today, but we're going to follow up with some folks, and we will get an answer to that before we post it by next week when we go to part 2 of the training. So whoever asked that, please, even though we're not answering it now, we will get an answer for you, and please do check with the Q&A doc when we post it to the training page. So question number 3, do you have world sea level records before 1993? If yes, where can we find that information?
Yes, we do. And most of the tide gauge data has been collected into one kind of database. And that data is all available through the Permanent Service for Mean Sea Level, PSMSL, which compiles tide gauge records from around the world and makes them available in one place. I've put the link there in the Q&A doc. The data is freely and openly available to the public, so you can go to that link and access all of the data there. And some of the tide gauge records go much further back in time before 1993. In fact, some tide gauge records have data back to the 1800s. So the answer is yes. There is data that goes back before 1993. It gets more sparse as you go back further in time, but all of the data can be downloaded there through PSMSL.
Terrific. Thank you, Dennis. Question number 4. How reliable is the sea level measurement from a satellite altimeter along the coastline, considering the degrading signal close to the coastline? What precautions should I take when using the data?
This is another very good question. So yes, in general, as satellite radar altimeters get measurements close to the coast, they can be corrupted by land and vegetation. And this happens when one radar footprint includes within it both ocean and land. So these footprints can vary in size. It depends on the satellite mission and the particulars of each instrument, but they can be somewhere on the order of a few kilometers to sometimes tens of kilometers in size. And so typically when we at NASA put together global gridded data products where we put together data from all of our radar altimeters to give a global gridded ocean sea surface height change around the world, we discard that data that's close to the coast. So within several tens of kilometers of the coast, typically that radar altimetry data is discarded for exactly this reason. I'm not really an expert in this. I'm sure there are ways to possibly make corrections for that. But again, when we do our global products, we typically discard that data for this exact reason.
Okay, thank you, Dennis. Question 5. Are projected tide gauge datasets directly available for download? And if so, through what platforms? Example given, NASA GitHub.
Yes, so this is another great question. So it depends on if this particular question is asking about historical tide gauge data or the projections at tide gauges. So as I answered before to a previous question, all of the historical sea levels from tide gauge measurements are available through that PSMSL data link. So that's the past, the historical measurements at tide gauges. We do make available sea level change projections at tide gauge locations, not all tide gauge locations, but certain, a large subset of them. And I think the best place to get those is from the IPCC AR6 sea level projection tool. It's on the NASA Sea Level Change Team web portal. I've put the link there in the chat. And the next part of this training will actually go through in detail how those projections are compiled and a little bit about how you can access them through this tool. But if you go to that link, you should be able to pull up a map of tide gauge locations, click on a particular tide gauge, and be able to download the projection data at that tide gauge location.
Okay, thank you, Dennis. Question 6. Can you add Guam to the Pacific Flooding Analysis tool? This person sees that they have Saipan within the Pacific Flooding Analysis tool, which is a Commonwealth of the Northern Mariana Islands. So they're curious about the island of Guam.
So I'm not privy to exactly the plans for this particular tool. I know that the functionality is being expanded to add more locations, but I'm not sure exactly which ones. And so it's possible that this location will be added as part of that tool and will be available in the future. But again, unfortunately, sorry, I can't speak to exactly which locations will be added. But I can do my best to track that information down and add it to this Q&A document after the training.
Great. And whoever asked the question, hopefully you can join us next week. Hopefully that is the intention. And certainly ask Dr. Phil Thompson. I think maybe Dennis, you might be able to answer that. But regardless, I hope you join next week and certainly resubmit that question because we should have somebody who might be able to answer at that time. Question number 7, with sea level rise, would there be any negative impact on coastal communities whose main economic activity is fishing?
So again, I think we'll have to circle back to that one and provide more information. I'm not the expert on fishery impacts. I can guess that the answer will be yes, although it's possible that it won't be directly through sea level rise, but rather through ocean circulation changes. That might be another driver of changes, as well as ocean warming. But we will try to track down a more direct answer to that question as well.
Okay, great. Question 8. Is it possible to retrieve sea level data for a specific location on Sea Level Explorer?
Yes, the answer is yes. So the Sea Level Explorer tool will provide information, will provide both historical and projected sea levels for specific cities and countries. That's kind of how that tool is framed around those sorts of locations. So if you're interested in looking at a specific city or the entire coastline of a country, that the Sea Level Explorer tool is the right place to go. As I mentioned before, the IPCC AR6 sea level projection tool, which we'll go over in the next part of the training, gives, I think, the easiest way to get sea level projections at tide gauge locations. So if you're looking at a particular tide gauge rather than, let's say, the entire coastline of a country, that IPCC AR6 tool may be the easiest place to go.
Okay, great. Question number 9. Has the East Antarctic ice sheet been losing ice mass in the last 2 decades? If yes, then at what rate?
This is a great question. And whoever asked this honed in specifically on East Antarctica. So in general, the Antarctic ice sheet, which is quite large, can be separated into different regions. Typically, what we do is separate it into East Antarctica, which is actually quite dry. There's not, on average, there's not a lot of precipitation in the form of snowfall that happens there. In fact, it's often called the world's largest desert because of a lack of precipitation. So even though it's an ice sheet, we consider it a desert because of the lack of precip there. So that's East Antarctica. Then we also have the Western Antarctic ice sheet and the peninsula. So those three regions make up the entire ice sheet. Over the last couple of decades, East Antarctica has actually gained mass. And this is sort of counterintuitive, but one kind of hypothesis is that in a warming climate, yes, we have air temperature that's warming and therefore driving melting of the ice sheets. But in addition to that, we also, because the air is warming, it can hold more moisture, and that actually can increase precipitation in certain parts of the world. And we think that's what might be driving more snowfall in East Antarctica and causing the eastern part of the ice sheet to actually gain mass over the last couple of decades. So East Antarctica is responsible actually for global sea level fall over that time period. Now, that does not balance out the losses that we're measuring in the other parts of the ice sheet, in the West Antarctica ice sheet and the peninsula. So because those other two regions are losing so much mass, the Antarctic ice sheet as a whole overall is losing mass. And over the last 2 decades has contributed to over 5 millimeters of global sea level rise. So even though the East is gaining mass, it's counterbalanced by the losses in mass in the other parts of the Antarctic ice sheet.
Great, thank you, Dennis. Question number 10. If we talk particularly about the Antarctic ice sheet, then does the choice of ice density matter in evaluating mass balance? Do we need to take different snow density values if we want to calculate the accurate mass balance using radar altimeters?
Yes, this is an excellent question and very much an open area of research. Converting altimetry information into mass requires us to know something about the density, because the altimeters really can only measure a volume change. And so to convert from volume change to mass, you need to know what the density is of the material that you're measuring underneath. This is pretty challenging, especially over Antarctica, which again is quite large, and bulk density of the snow and ice column that's underneath of our altimetry measurements is not something that we can measure from space. So we rely on ground-based measurements and models to sort of fill in the blanks and give us an estimate of the density of the snow and ice that's underneath of each altimetry measurement. So because Antarctica in particular is large, remote, very difficult to get to, hard to do field work there, these ground-based measurements of density are pretty sparse on the ice sheet. And so this adds a layer of uncertainty when we convert altimetry measurements into mass measurements. So yes, the answer is we do need to take into account different densities of snow and ice underneath of the altimetry measurements. This is done through a combination of ground-based measurements and models. And nowadays the models are becoming better, and we are able to get a pretty good estimate of the mass change from altimetry, but this is still a source of uncertainty in those measurements.
Terrific. Yeah, great question and really great answer as well. Thank you, Dennis. Question 11, maybe somewhat similar in terms of the answer, but the panelists emphasize the combination of altimetry and tide gauge data in measuring sea level rise. How is this done in areas with no tide gauges? For instance, the entire West African coastline has just 5 tide gauges.
Yes, this is a good question. And I guess the short answer is in places where we don't have tide gauges, we have to rely pretty much completely on satellite measurements, as well as models. The global ocean models that we typically use give us a very good look at global ocean circulation. And but when you get close to the coast, there can be kind of detailed coastal ocean circulation and dynamics that aren't necessarily taken into account in those models. So it's definitely challenging in places where we don't have that ground truth from the tide gauges. And yeah, those are places where we have to rely on satellite data and models. And in data sets like projection data sets where we don't have tide gauges, our uncertainties on what will happen in the future are larger than in places where we do have tide gauges. So we can still make projections to try and look into the future and project what will happen in places where there are no tide gauges. But in those places, we have larger uncertainties because we don't have that ground truth.
Terrific. Thank you so much, Dennis. Question number 12. I visited the NASA Sea Surface Height website. There are different sea surface height products on the site. Could you please explain the data set and which is most appropriate to monitor absolute sea level?
Yeah, this is a great question. And to be honest, we get questions like this a lot because we produce a lot of data from our satellites, and it's often not exactly clear which ones are the right ones to use for a particular problem. I think what we can do is answer this offline. So after the training, we can put in a pretty thorough answer here that hopefully describes the different sea surface height data sets and points you in the right direction. One kind of general answer that I could say is that with NASA satellite data sets, sometimes what you'll see is they're described in terms of processing levels. So we have level 0, level 1, 2, 3, and 4. And basically, the higher the processing level, the more processing has been done to it. So level 0 data sets you probably won't even find on the web because they're not really useful for science or applications. Those are like raw voltages that the instruments on the satellites are measuring. Then as you move further into the processing, you get into more of the geophysical variables. So for example, a level 2 data set may be a point estimate of the surface elevation at a certain time underneath of a radar altimetry footprint. Then if you go higher in the processing level, so go to level 3, for example, level 3 data products are typically our gridded data products. So that's where we take all of those point measurements from the altimeters and grid them and sometimes interpolate to fill in the blanks and give output global gridded data products. So one thing you can look for is those processing levels. And if you're interested in, for example, a global picture of sea surface height where all of the gaps are filled in time, your best bet is to look for a level 3 data product. If you're interested in point measurements of what our satellites measured at a very specific location and at a very specific time, you can look at the level 2 or sometimes maybe level 1 data products. So that's a general answer. But with the sea surface height data sets, like I said, we'll come back and try to fill in the blanks with some specific information there.
Great. Thank you, Dennis. Question 13. Is sea level rise unavoidable? The last 3 decades record shows that the sea level is steadily rising. Though the scientific community is trying hard to give awareness to world leaders, nothing is working out significantly to reduce global warming.
This is a good question. So the short answer is sea level rise is not unavoidable based on our understanding of how the Earth system is working and what's contributing to sea level rise. There are future emissions pathways that would put us on a net sea level fall, for example, over the next century. The next part of the training, part 2 of this training, Dr. Bob Kopp will go into a lot of the detail, more detail on how the different scenarios and emissions pathways are kind of designed in the IPCC assessment report. Some of those futures are sort of a worst case scenario where we continue to use fossil fuels and emit the way that we have been for the last several decades. Some of those scenarios are, let's say, a best case scenario where we switch away from fossil fuels and toward clean energy. And so, and then there are some scenarios in between. So it's not unavoidable. I can't speak to how likely it is that we're on any given one of those scenarios in the future. It depends on human decision making. But yeah, part 2 of the training will go into more detail there, and hopefully that'll give you a better understanding of kind of these different futures that we're faced with and how sea level rise looks under each of those different scenarios.
Well, thank you, Dennis. Looking at the time, we are at the conclusion of today's part 1 of the webinar. I want to thank everybody for joining, and especially those that asked these really terrific questions. Unfortunately, Angelica Rodriguez had to drop off, so she's no longer on. But Dennis, as we wrap up part 1 and we look forward to part 2, I just wanted to know if you had any maybe closing thoughts or comments you wanted to share before we wrap things up. So over to you.
Thanks, Sean. I want to thank everybody for joining for this training, and thank you all for your questions. If, as Sean said earlier, if you have a question that wasn't answered satisfactorily, or you have a follow-up question, please do join us for the next part of the training and re-ask or reframe or ask us a follow-up question. We're happy to answer these, and we'll get to all of them in more detail after the training. So we're definitely looking forward to having you all join us in part 2, where we'll go into more of the projection side of things, and as well as the coastal flooding impacts and the tools that you can access that information. So thank you very much, and look forward to seeing you in the next part.
Great. And Dr. Felikson, thank you again so much. Such an amazing presentation and demonstration. So thank you. And also Dr. Rodriguez, unfortunately, she had to drop off, but we want to definitely thank her once again. And also to the ARSET team. You might not have heard their voice or seen their face, but that's Natasha Johnson-Griffin, Brock Blevins, Selwyn Hudson-Odoi, and Jonathan O'Brien. So thank you so much to the ARSET team. And we look forward to seeing you all next week on Tuesday, June 17th for the second part of the webinar series. Thank you, everybody.